Hey folks, today we're going to talk about gas laws, Boyle's, Charles, Gay-Lussac's laws. So you're going to need your calculator and you're going to need to take some notes. Alright, let's start here looking at standard temperature and pressure. You know these. Standard temperature is 0 degrees Celsius or 273 Kelvin, and you need to be able to convert between these two measurements. Right? You also need to be able to convert between all of these different pressures. That's something we did in the last podcast, so you need to make sure you know how to do that. Alright, what we are going to do today is we're going to go through these podcasts. Right there for Boyle's law, Charles' law, and Gay-Lussac's law. That's in this podcast. The combined gas law is the next podcast. Avogadro's and ideal is the following one. And Graham's law and Dalton's law of partial pressure is the next one. So we have a lot of different laws we're going to talk about that have to do with gases. So let's get started with Boyle's law. Boyle's law is talking about you have an initial system, which is P1V1, and it changes to P2V2. In other words, you're starting with a particular pressure and volume. You have a closed system, and you change, let's say, the pressure, and that means the volume has to change. Okay? So, the way this works is the pressure and the volume of a sample of gas at constant temperature. This is the key, constant temperature, and they're inversely proportional, meaning as one goes up, the other goes down. So if you know 3 of the 4 values, you can calculate the 4th one. Right? So let's give you an example of what this looks like a little bit. Okay? We're going to go and run this little thing. So you'll notice what's happening is we're going to compress this, and so we're going to make it smaller, so we're going to change the volume here. So we compress it, and you'll notice the volume changes and our pressure changes. Our temperature remains constant, but our pressure is changing. So if we expand it now, the pressure is going to go back down to what it used to be because our volume changes to what it used to be. The key here is your temperature is remaining constant. Okay? That's what all this is all about. Alright, so a more fun example that you'd be familiar with is popping a water bottle. You know how you squeeze a water bottle and turn it until the cap finally flies off? The temperature of the air inside is pretty much the same as it was. The difference is that the pressure is changing. Clearly the volume is changing. Okay, so let's go ahead and do a mathematical example of this. We have P1V1 equals P2V2. That's Boyle's law. And we have an initial volume here of 8.5 liters and an initial pressure of 0.980 atms. And we're changing the pressure to 1.30 atms. Now before I go any further, notice that your units here are both atmospheric pressure. The units don't matter so long as the units are the same. So if we were doing this with kilopascals or we were doing this with millimeters of mercury, wouldn't make any difference so long as the units are the same. Now you can't mix atms and millimeters of mercury. In that case you have to choose one and do your math in one and then convert to the other. But so long as your units are the same, so long as you're consistent, that's fine. Alright, so let's plug some values in. We start with a pressure of 0.980 atm, and we're multiplying by 8.50 liters, and that's going to equal a new pressure of 1.30 atm, and some unknown number of liters. Now, pause the video, see if mathematically you can work that out. Alright, folks, this should be pretty easy for you. You should know that all you have to do is multiply these two things on the left and divide by the 1.30. Alright, so I'm going to write this one out, and after that I'm not going to write them out anymore because I don't want to waste your time or mine. 8.50 liters. Alright, but when you're doing this, make sure you write down the units when you actually do this. Alright, because what you should notice is you've got atms here and atms here, and they cancel, and you're left with liters, which is the answer that you want. Right? And that really helps you make sure that you didn't mess up as you went through this. Alright, so your answer here is going to be 6.41 liters. Notice I have 3 sig figs in all my numbers, so my answer has 3 sig figs. Okay. Let's go on to Charles's law. Charles's law is different. is it says we're keeping the pressure constant. So you'll notice the pressure is never mentioned up here in the problem, and that's because the pressure is constant. So it says at a constant pressure, the volume of a fixed amount of gas is directly proportional to its absolute temperature. So again, so long as I have a closed system and I do not change the pressure, then my volume and temperature are directly proportional, meaning as one goes up, the other goes up. All right, so let's look, for example, at Charles's law. Charles's law says I'm going to heat this up. When I heat it up, notice my temperature goes up and my volume goes up, but my pressure is remaining the same. So it went up from 10 liters to 20 liters. Now, so long as my pressure remains the same, I cool it down, my temperature is going to go down, my volume is going to go down as well. Okay. Again, I have a closed system. I didn't add any molecules to this at all. The number of molecules in there, the amount of gas remain the same. Okay. A more fun example would be a hot air balloon. So when you think of a hot air balloon, we heat it up with a flame down here. So what's happened to these molecules in here is they've gotten further apart. They're moving faster. They're pushing out on the balloon. But since this is an open system, the air is coming out of here. The excess air is coming out. So the pressure inside the balloon is remaining the same. So the pressure never changed. Okay, but the volume did because all of these air molecules came pushing out of the balloon. Right? So let's actually do a problem with Charles's law. Now this problem with Charles's law is, remember, it's a closed system. The air is not allowed to escape. All right. So we have an initial temperature of 25 Celsius and a volume of 1.82 liters is heated to a temperature of 50 degrees Celsius. So we have, what's the final volume? So we have your initial volume over your initial temperature is equal to your final volume over your final temperature. Now, it's going to be real tempting to write 1.82 liters divided by 25 Celsius is equal to some number of liters over 50 Celsius. And this is wrong. Why is it wrong? Well, it's wrong because your temperatures are wrong. Your temperatures have to be in Kelvin. Oh gosh, yes. So let's look at our first temperature. Our first temperature is 25 degrees Celsius. But remember, it has to be in Kelvin. So we have to add 273 to that. Right? And when we do that, we get 298 Kelvin. And our final temperature, which is 50 degrees Celsius, we have to add 273 to that. So that's going to give us 323 Kelvin. Now we can do the problem. So now we say 1.82 liters divided by 298 Kelvin is equal to some number of liters over 323 Kelvin. All right. Pause the video, see if you can do the math. Okay, folks, when you do the math, you should be multiplying, you should be cross-multiplying, you should be multiplying the 1.82 times the 323, and then dividing by the remaining thing, which is 298. So your answer here is going to be 1.97 liters. All right, let's go on to Gay-Lussac's law. This looks surprisingly like Charles's law. It's very, very simple. Here we are keeping a constant volume. So now our pressure is changing. So the pressure is changing, and the pressure, like the volume, is directly proportional to the temperature. So as the temperature goes up, the pressure goes up. Okay, that's what this means. So again, let's look at one of these cute little demonstrations here, Gay-Lussac's law. And it says, as we heat it up, the pressure changes. Notice our volume is remaining constant. Our pressure is changing. What's happening is the molecules are hitting so much harder. They're moving so much faster. They're creating far more pressure inside the system. So your pressure has gone up. So when you cool it down, the molecules slow down. When the molecules slow down, the pressure goes back down. Now, if we if we make this cooler even still, the pressure is going to go down further because the molecules are going to slow down even further. Okay. All right, a more fun example might be taking an aerosol can, please don't do this at home, taking an aerosol can and throwing it in a fire. Now once that aerosol can has a lot of pressure in it, okay, but if you throw it in a fire, what happens is it gets hot. And if you notice something on the back of the can, it says, do not allow the can to get over 120 degrees. And that's because the stuff inside builds up pressure and it will cause the can to explode. So let's go ahead and look at an application of Gay-Lussac's law. We have a neon sample with an initial temperature of 0 and a pressure of 3.50 atm. It's heated to a temperature of 100. What's the final pressure? Right? Well, what we're working with is P1 over T1. Your initial pressure over your initial temperature is equal to your final pressure over your final temperature. Right? They are directly related. So, go ahead and pause the video, see if you can plug these in and do it. All right, hopefully the first thing you did was you noticed your temperature was in Celsius. And if you have 0 degrees Celsius, you have to add 273 to it. So that becomes 273 for your initial temperature. And your final temperature would be 373. And our initial pressure is 3.50 atms. So 3.50 atms divided by 273, and that's in Kelvin, is going to give you some number of atms, and it's going to be over 373. Now you'll notice I didn't tell you what I wanted the final pressure in. That's okay. If I don't tell you, you can assume whatever you want. Now since I'm given atms to start, I'm going to assume atms is going to work when we're done. Alright, so how do we solve this? Well, we cross multiply. So we have the 3.50 atms. We've multiplied by it 373 Kelvin. Now we're going to divide by what's left, which is 273 Kelvin. You should know how to cross multiply. And when I multiply all these things out, I get 4.78 atms. Alright, so this is easy, right? Yeah, it is. It really is. But guys, you have to make sure of a few things. The first thing is, you always must remember that your temperatures must be in Kelvin. And you have to make sure that your units for pressure and volume always match. And then the key here is, which equation do I use? Do I use Boyle's law, Charles' law, or Gay-Lussac's law? Well, what's important here is you step back and think first. And that's important. You really have to step back and think about this. Now, there are often multiple ways to solve a problem, and we're going to do one of those in a second. The bottom line is you have to step back and think about what you're doing. We're now getting into the thinking phase of chemistry, where you have a bunch of equations. You have to know which one to use. All right, so here's a problem. You have a 5.2 liter metal container. It's filled with air at a temperature of 18 Celsius and a pressure of 122 kPa. It's left in the sun. What's the pressure inside the container in millimeters of mercury a few hours later if the temperature has risen to 37 degrees Celsius? Okay, pause the video, see if you can figure out which equation to use, and try and set it up. Give it a moment and see if you can set it up. Okay, so let's look at what we have. We notice that we have something that's at 18 degrees Celsius, and its temperature is changing to 37 degrees Celsius. Well, that means my temperature is not constant, so that throws out Boyle's law right there. Right? So the question is, do I use Charles or Gay-Lussac's? Well, I have a pressure of 122 kPa, and I have a 5.72 liter metal container. So, what's changing? Well, it's asking me what is the pressure inside the container. So my pressure's changing. So my pressure's changing. My temperature's changing. How about my volume? Well, it's a metal container, so it's probably not changing in size. So bottom line is, my pressure's changing, my temperature's changing, and my volume is not changing. So I'm going to use something that includes pressure and temperature. That's Gay-Lussac's law, right? And so I should be able to work with this. Now, I do notice, again, before I start, I look at this and I notice that I'm given information in kPAs, and I want to know my answer in millimeters of mercury. And we've said we can't do that. So we have to stick with either kPAs or we have to stick with millimeters of mercury. So I'm going to do this problem two ways. I'm going to start with kPAs. All right, what I'm going to do is I'm going to do my math in kPAs, and then I'm eventually going to change to millimeters of mercury. So let's go ahead and plug this in and see what happens. Well, my first thing I have to do is my temperature is equal to 18 degrees Celsius to start. So I add 273 to that, and that gives me 291 Kelvin. And I do the same thing with my second temperature, which is 37 degrees Celsius. I add 273 to that, and I get 310 Kelvin. All right, so those are my temperatures. My pressure is 122 kPa, and I put that over 291 Kelvin, and that's giving me some unknown number of pressure, and my pressure is going to be in kPa. My units must remain the same. Right. So now pause the video and do the math, see what you come up with. All right, I come up with about 130 kPa is my answer. Right. Now, when I come up with 130 kPa, remember you're cross-multiplying here, right? I'm not done, and I'm not done because I want my answer in millimeters of mercury. So I have to take my 130 kPa, and I have to convert from kPa to millimeters of mercury. Now, the problem is I can't do that. Right? When I look at kPAs, I can't convert directly to millimeters of mercury, but what I can do, if you go back to your chart of conversion factors, which we did in the last podcast, you can see that you can go to ATMs, and then from ATMs, you can go to millimeters of mercury. So that's what I'm going to do. I'm going to convert from kPAs to ATMs, and then I'm going to convert from ATMs to millimeters of mercury. Guys, what you're doing is you're starting to put pieces together. That's what this is all about. All right, well, one ATM is 101.325 kilopascals, and one ATM is 760 millimeters of mercury. So if I sit there and I multiply across the top and divide by the bottom, I get 975 millimeters of mercury. And that's the answer. Okay. I said there were two ways to do this. I said we could either do our math in kPAs or we could do our math in millimeters of mercury. So I'm going to do this problem again on the next slide. We do want to remember what our temperatures are because I don't want to have to go through that calculation again. So this is the identical question. So we're going to start this time with 122 kPa, but what I'm going to do is I'm going to immediately convert the 122 kPa. I'm going to immediately convert that from kPAs to atmospheres, and from atmospheres to millimeters of mercury. So I'm going to do that first. We know that one atmosphere is 101.325 kilopascals, and one atmosphere is 760 millimeters of mercury. All right, so this time I go through the math here, and I come up with my starting value is 915 millimeters of mercury. That's a number you haven't seen before. So we just went through the math to convert to millimeters of mercury first so that when I'm done using my Gay-Lussac's law, I'll come up with millimeters of mercury. All right, so let's go ahead and do that. We start with 915 millimeters of mercury. And that's going to equal some number of millimeters of mercury. Remember, we have to be consistent in our units. And our numbers on the bottom, if you remember, we did this a moment ago, is 291 Kelvin and 310 Kelvin. So now if I do my math out, and I do my cross multiplication, right, I end up with 975 millimeters of mercury, which is exactly the same answer we got in the last one, but I did it differently. So my point here is, if you think this through, there are multiple ways to solve the problem. So you have to figure out the way that best makes sense to you. All right, so we're done. As you look at the worksheet that you're going to be doing, the worksheet gets progressively harder. So if you do the first 2 or 3 problems and say, I'm done, don't stop there. Make sure you get to the end of the worksheet, because those include far more conversions thrown in, and not just using a straight Gay-Lussac's law, or Boyle's, or whatever. All right? Thanks. See you in class. If you have questions, let me know, or let us know. We'll be happy to help in any way we can. Take care.